Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum by Lee Smolin. Preface. We human beings have always had a problem with the boundary between reality and fantasy. To explain the world to ourselves, we make up stories and then, because we are good storytellers, we get infatuated by them and confuse our representations of the world with the world itself. This confusion afflicts scientists as much as lay people. Indeed, it affects us more, because we have such powerful stories in our toolkits. As we do go deeper into our understanding of the natural world, moving to smaller and more elementary phenomena, our successes impose barriers to further progress. To avoid getting stuck, we must balance our well-justified confidence in the power of established knowledge with an acute consciousness of just how hypothetical even our most successful hypotheses are. A hard lesson to learn is that our sensations are partly caused by reality, but are fully constructed by our brains to present the world to us in just the form we need to make our way in nature. Beyond those sensations, nature hovers, fundamentally mysterious and just at the edge of what we can know. The most important features of nature, as we understand them now, were not perceived. The simplest general facts we know about the world: the matter is made of atoms. For example, or that the earth is a spherical shell of a rock surrounding a molten core and enveloped within a thin atmosphere, which moves suspended in a near vacuum as it obeys a natural thermonuclear reactor. These plain facts we learned just after our trips are the result of centuries of intense effort by scholars and scientists. Each of these facts arose as an almost crazy idea in conflict with a much more obvious and reasonable but wrong hypothesis. To have a scientific mind is to respect consensus facts, which are the resolution of generations of dispute, while maintaining an open mind about the still unknown. It helps to have a humble sense of the essential mystery of the world, for the aspects that are known become even more mysterious when we examine them further. The more we know, the more curious it all is. There is not a thing in nature so ordinary that its contemplation cannot be a route to a world-less sense of wonder and gratitude just to be a part of it all. This spring morning, the air coming through the open window carries fresh smells from the garden. But by what miracle does that happen? How are molecules wafted by a breeze turned by a nose into that happy scent? We see vivid colors, and we recall that there is a story about how different wavelengths of light excite different neurons. But how could the sensations of redness or blueness possibly be caused by different neurons being excited? What kinds of things are the sensations, the qualia, as the philosophers call them? Or the different colors, or the different signs? In what way are scents different from colors, and why do they differ? If it is all electrical impulses in neurons, who is the I that wakes, and what is the universe that surrounds me when I open my eyes? The simplest facts about our existence and our relationship to the world are mysteries. Let us tiptoe past the hard question of a consciousness to simpler questions. As a scientist, I believe that is the best way to get somewhere. Let's start with one very basic question. What is the matter? My son had left a rock on the table. I picked it up. Its weight and shape fit comfortably in my hand, surely an ancient feeling. But what is a rock? We know what the rock looks like, what it feels like, but these are at least as much about us as they are about the rock. Little in a rock's feel or appearance gives a hint as to what essentially constitutes the existence, the rockness of a rock. We know most of the rock is empty space in which atoms are arranged. The solidity and hardness of the rock is a construction of our minds, which integrate perceptions on scales very coarse compared to the sizes of the atoms. Matter comes in many forms, some of which, like the rock, like the organic material woven into our blankets, sheets, and clothings, we know must be complex. So let's consider first a simpler form of a matter, the water in our glass. What is it? To our eyes and to our touch, water appears to be smooth, continuous, until relatively recently, a bit more than a century ago. Physicists thought that matter was entirely continuous. Early in the 20th century, Albert Einstein showed that was wrong and that water is made of a myriad of atoms. In water, these are organized into triplets, bound together into molecules, each consisting of 2 hydrogen and 1 oxygen. Yes, but what is an atom? It took less than a decade after Einstein for it to be understood that each atom is like a tiny solar system, with a nucleus in the center in place of the sun and the planets represented by electrons. So far, so good. But then, what is an electron? We know that electrons come in discrete units, each one carrying a certain quantity of mass and charge. An electron can have a location in space. It can move. When we first look at it, it is here. When we look again, it is there. Beyond those attributes, it is not easy to give a picture of what an electron is. It will take much of this book. The best understanding of what rocks are, what water is, what molecules and atoms and electrons are, is expressed by the branch of science called quantum physics. But as it seems everyone knows by now, that is a realm full of paradox and mystery. Quantum physics describes a world in which nothing has a stable existence. An atom or an electron may be a wave or a particle, depending on how you look at it. Cats are both alive and dead. This is great for popular culture, which has made quantum a buzzword for cool, geek mystification. But it's terrible for those of us who want to understand the world we live in, for there seems to be no easy answer to the simple question, what is a rock? In the first quarter of the 20th century, a theory called quantum mechanics was developed to explain quantum physics. This theory has been, ever since its inception, the golden child of science. It is the basis of our understanding of atoms, radiation, and so much else. From the elementary particles and the basic forces to the behavior of materials. It also has been for just as long a troubled child. From the beginning, its inventors were deeply split over what to make of it. Some expressed shock and misgivings, even outrage. Others declared it a revolutionary new kind of science, which shattered the metaphysical assumptions about nature and our relationship to it that the previous generations had thought essential for the success of science. In these chapters, I hope to convince you that the conceptual problems and raging disagreements that have bedeviled quantum mechanics since its inception are unsolved and unsolvable, for the simple reason that the theory is wrong. It is highly successful but incomplete. Our task, if we are to have simple answers to our simple questions about what rocks are, must be to go beyond quantum mechanics to a description of the world on an atomic scale that makes sense. This task might seem overwhelmingly difficult, were it not for one almost forgotten and long-ignored aspect of the history of quantum mechanics. Since the very beginning of the quantum era, in the 1920s, there has been an alternative version of quantum physics that does not make a complete sense. This shadow theory resolves the apparent paradoxes and mysteries of the quantum domain. The scandal, and I believe the term is warranted, is that this alternative form of quantum theory is rarely taught. It is seldom mentioned, either in textbooks for budding physicists or in popularizations for lay people. There are several alternative formulations of quantum physics that make consistent sense. The challenge now is to build on these to find the right way to understand quantum physics. The one that nature uses, I believe this will have wide repercussions. Because a new form of quantum physics will be the basis of the solution to many of the outstanding problems in physics. Problems such as quantum gravity and the unification of the forces, in which we have made little definitive progress, are, I believe, foundering because at the foundations of our theorizing is an incorrect theory. Physicists agree about how the quantum world behaves. We agree that atoms and radiation behave differently than rocks and cats. And we agree that quantum mechanics works to predict some aspects of that behavior. But we don't agree about what it means that our world is a quantum world. It is clear that some radical change in our understanding of nature is required. But we disagree as to what that change needs to be. Some argue that we must give up holding any picture of a reality and settle for a theory which describes only the knowledge we can have of the world. Others claim that our notion of reality must be vastly extended to embrace an infinitude of parallel realities. In fact, neither is necessary. The alternative ways of understanding the quantum world do not require us to give up the idea that physics describes a reality independent of our knowledge of it, nor do they require that we expand that reality beyond the common sense notion that there is one world and it is what we see when we look around us. As I will explain in these pages, common sense realism, according to which science can aspire to give a complete picture of the natural world as it is, or would be in our absence is not actually threatened by anything we know about quantum physics. It is thus both unfortunate and unnecessary that the quantum realm has been presented as mysterious and counterintuitive. One of the aims of this book is to present the alternative quantum theory to lay people, and by doing so, to lift the mystery and present the quantum world in a way that is intuitive and accessible to people who are not specialists in physics. I imagine my reader as someone with a strong curiosity about nature, who may follow science through news, blogs, and popular books, but whose education has not included the mathematics usually assumed as the language of physics. Instead, I use words and pictures to convey the basic phenomena we find in quantum world, as well as the principles their study has inspired. After an introduction, the book starts with 3 short chapters which describe the bare bones basics of quantum physics. This will equip us to explore the diverse conceptual universes which arise from the different forms of quantum theory that have been proposed. What is at stake in the argument over quantum mechanics? Why does it matter if our fundamental theory of the natural world is mysterious and paradoxical? Behind the century-long argument over quantum mechanics is a fundamental disagreement about the nature of reality, a disagreement which, unresolved, escalates into an argument about the nature of science. 2 questions underlie the schism. First off, does the natural world exist independently of our minds? More precisely, does matter have a stable set of properties in and of itself, without regard to our perceptions and knowledge? Second, can those properties be comprehended and described by us? Can we understand enough about the laws of nature to explain the history of our universe and predict its future? The answers we give to these 2 questions have implications for larger questions about the nature and aim of science, and the role of science in the larger human project. These are indeed questions about the boundary between reality and fantasy. People who answer yes to these 2 questions are called realists. Einstein was a realist. I'm also a realist. We realists believe that there is a real world out there whose properties in no way depend on our knowledge or perception of it. We realists believe that there is a real world out there whose properties in no way depend on our knowledge or perception of it. This is nature, as it would be and mostly is in our absence. We also believe that the world may be understood and described precisely enough to explain how any system in the natural world behaves. If you are a realist, you believe that science is the systematic search for that explanation. This is based on a naive notion of truth. Assertions about objects or systems in nature are true to the extent that they correspond to genuine properties of nature. If you answer not to one or both of these questions, you are an anti-realist. Most scientists are realists about everyday objects on the human scale. Things we can see, pick up, and throw around have simple and easily comprehended properties. They exist at each moment somewhere in space. When they move, they follow a trajectory, and that trajectory has, relative to someone describing them, a definite speed. they have a mass and a weight. When we tell our partner that the red notebook they are looking for is on the table, we expect that this is simply true or false, absolutely independent of our knowledge or perception. The description of a matter at this level, from the smallest scales we can see with our eyes up to stars and the planets, is called classical physics. It was invented by Galileo, Kepler, and Newton. Einstein's theory of relativity are its crowning achievement. But it is not easy or obvious for us to be realists about a matter on the scale of individual atoms. This is because of quantum mechanics. Quantum mechanics is presently our best theory of nature at the atomic scale. The theory has, as I have alluded to, certain very puzzling features. It is widely believed that those features preclude realism. That is, quantum mechanics requires that we say no to one or both of the two questions I asked above. To the extent that quantum mechanics is the correct description of nature, we are forced to give up realism. Most physicists are not realists about atoms, radiation, and elementary particles. Their belief, for the most part, does not stem from a desire to reject realism on the basis of radical philosophical positions. Instead, it is because they are convinced quantum mechanics is correct, and they believe, as they have been taught, that quantum mechanics precludes realism. If it is true that quantum mechanics requires that we give up realism, then if you are a realist, you must believe that quantum mechanics is false. It may be temporarily successful, but it cannot be the fully correct description of nature at an atomic scale. This led Einstein to reject quantum mechanics as anything more than a temporary expedient. Einstein and other realists believed that quantum mechanics gives us an incomplete description of nature, which is missing features necessary for a full understanding of the world. Einstein sometimes imagined that there were hidden variables which would complete the description of the world given by quantum theory. We believed that the full description, including those missing features, would be consistent with realism. Thus, if you are a realist and a physicist, there is one overriding imperative, which is to go beyond quantum mechanics to discover those missing features and use that knowledge to construct a true theory of the atoms. This was Einstein's unfinished mission, and it is mine. There are different kinds of anti-realists, which leads to different views on quantum mechanics. Some anti-realists believe that the properties we ascribe to atoms and elementary particles are not inherent in those objects, but are created only by our interaction with them, and exist only at the time when we measure them. We can call these radical anti-realists. The most influential of these was Niels Bohr. He was the first to apply quantum theory to the atom, after which he became the leader and mentor to the next generation of quantum revolutionaries. His radical anti-realism colored much of how quantum theory came to be understood. Another group of anti-realists believe that science as a whole does not deal in or talk about what is real in nature, but rather only ever talks about our knowledge of the world. In their view, the properties physics ascribes to an atom are not about the atom. They are instead only about the knowledge we have of the atom. These scientists can be called quantum epistemologists. Epistemologists. It's difficult to pronounce that. And then there are the operationalists, a group of anti-realists who are agnostic about whether there is a fundamental reality independent of us or not. Quantum mechanics, they argue, is not, in any case, about reality. It is rather a set of procedures for interrogating atoms. It is not about the atoms themselves. It is about what happens when atoms come into contact with the big devices we use to measure them. Heisenberg, the best of Bohr's proteges, who invented the equations of quantum mechanics, was at least partly operationalist. In contrast to the dispute between radical anti-realists, quantum epistemologists and operationalists, all realists share a similar perspective. We agree about the answer to both questions I pose above, but we differ on how we answer a third question. Does the natural world consist mainly of the kinds of objects that we see when we look around ourselves, and the things that constitute them? In other words, is what we see when we look around typical of the universe as a whole? Those of us who say yes to this question can call ourselves simple or naive realists. I should alert the reader that I use the adjective naive to mean strong, fresh, uncomplicated. For me, a view is naive if it is not in need of sophisticated arguments or convoluted justifications. I would argue that a naive realism is, whenever possible, to be preferred. There are realists who are not naive in this sense. They believe that reality is vastly different from the world we perceive and measure. An example of such a view is the many worlds interpretation, which teaches that the world we perceive is only one of a vast and ever-growing number of parallel worlds. Its proponents call themselves realists, and they have some claim to that designation by virtue of their answering yes to the first two questions. But in my opinion, they are realists only in the most technical, academic sense. They may perhaps be called magical realists, for they believe that what is real is far beyond the world we perceive. Magical realism, in this sense, is almost a form of mysticism, for it implies that the true world is hidden from our perception. Is it possible to formulate a theory of atoms that is a realist in the most general and naive sense, and so answers yes to all three questions? It is, and that is the story I want to tell you in this book. But that theory is not quantum mechanics, and if it is right, then quantum mechanics is wrong, in the sense that quantum mechanics must then give a very incomplete description of nature. Part of the theory I want to tell here is how this naively realistic theory of nature was pushed aside, while a theory that required us to embrace either anti-realism or mysticism thrived. But I will end on a hopeful note by sketching a way we may progress to a realistic view of nature that encompasses the quantum. I think I should stop here because I still have several pages to go. I just want to give a view of my own about this. I believe that this realistic view someone is talking about will not be achieved because it is convoluted. I'm more like in the Copenhagen school, as Niels Bohr is championing, because that theory is not only the simplest, which I feel is kind of true according to the Reiser rule. That is anything that's real, it is more likely to be true. Anything that is convoluted is more likely to be wrong. Second, I believe that Salomon is using the word realistic, reality, in a way too narrow. That's why he believe other people are not realists. Because I feel that the nature of the nature is indeed a quantum. It does not depend on how we look at it. It depends on how we look at it only when we want to get some view of it. The nature itself is, as what quantum mechanics described, more concretely, it has many different phases. It's a multi-phases. It's like a particle, which can be a particle and also can be a wave. The nature itself is like that, but that's the reality. But the reason that when we look at this thing, it can either be a particle or a wave, is just a way that we access to the nature. It does not mean we affect the nature. The nature is there. So that's my view, but I don't want to talk too much on that. People who understand me will understand. People who do not understand me may feel confused. So I will stop here, and the rest of this preface will be read later on. There are still like 3 or 4 pages.